There is light that is older than all stars, galaxies, and planets. It appeared when the universe first became transparent, and space was not yet like the dark and almost silent cosmos that we see today. The Milky Way, the solar system, and even the first stars did not exist. The entire cosmos was filled with hot, dense plasma in which light could not move freely. Photons constantly collided with charged particles, scattered, and disappeared again in the blinding fog of the young universe. This continued for about 380,000 years after the Big Bang. Space expanded, the temperature decreased, and free electrons began to combine with protons to form neutral hydrogen atoms. Almost instantly, by cosmic standards, the opaque plasma dissipated. Light, which had previously been locked within incandescent matter, was able to move through space. This ancient light still surrounds us from all sides.
Over billions of years, the expansion of the universe has stretched its waves. It was once bright and hot, but gradually shifted to the microwave region of the spectrum. Today, it is called the CMB, or Cosmic Microwave Background. It's not just a distant glow. This is the oldest picture of the universe that we are able to see, a boundary of light beyond which conventional telescopes can no longer show us earlier eras. The temperature of this radiation is about 2.7 degrees above absolute zero. It fills the entire sky, and at first glance seems almost perfectly homogeneous. However, this homogeneity is not absolute. In different directions, the temperature differs by negligible values, only by tens of microkelvins. It was these tiny differences that became the basis of the future structure of the cosmos.
Where the density of matter was slightly higher, gravity gradually collected more and more matter. Hundreds of millions of years later, the first stars and galaxies appeared in these regions. Then clusters of galaxies, giant filaments, and huge voids of the cosmic web appeared. The entire diversity of the observable universe grew out of barely noticeable inhomogeneities left on the map of the CMB radiation. This map was supposed to be almost completely predictable. Cold and hot areas are randomly distributed over it, obeying known statistical laws. Most of them are in perfect agreement with the modern cosmological model. But in one direction, this pattern seems to be violated. In the constellation Eridanus, there is a huge region, the temperature of which is noticeably lower than the surrounding background. It occupies a few degrees of the sky and looks too large and too cold for a normal wobble of this magnitude. This anomaly is called the cold spot of cosmic background radiation.
This is where one of the strangest mysteries of modern cosmology begins. The cold spot was discovered during the analysis of data from the WMAP spacecraft. Later, its existence was confirmed by more accurate observations of the Planck mission. This meant that the anomaly was not a simple malfunction of the instrument or random noise in the data. It is indeed present on the ancient map of the sky. However, the mere existence of a spot does not mean that an unknown cosmic phenomenon is hidden behind it. On a huge map containing countless temperature fluctuations, there is bound to be the coldest area. Even a completely random distribution sometimes creates structures that look unusual. Therefore, the most cautious explanation is that the cold spot is a rare but permissible statistical fluctuation. This explanation remains one of the most likely. And yet, it does not close the issue completely.
Not only is the temperature of the spot unusual, but also its huge angular size. Depending on how you analyze the data and take into account the selection of the coldest area in the entire sky, the statistical significance changes. Some calculations show that such a structure could have arisen by accident. Others point out that the probability of such a coincidence is small enough to continue the search for a physical cause. If the cause really exists, it must be either between us and the CMB radiation, or it must be related to processes that took place at the earliest moments in the history of the universe. The first and most natural explanation has to do with a gigantic cosmic void. The universe is filled with matter unevenly. Galaxies form long filaments, dense knots, and huge clusters. In between lie regions in which galaxies and dark matter are much smaller than average.
Such areas are called voids. Some of them reach hundreds of millions of light years across and occupy colossal volumes of space. If a photon of the CMB passes through such a void, its energy may change slightly. The reason is related to the expansion of the universe and a change in gravitational potential during the movement of light. In an unchanging space, the energy losses and gains of the photon would be fully compensated. But the universe is expanding, so the compensation is incomplete. As a result, a photon that has passed through a large void can reach us a little less energetic and look colder. This process is called the integrated Sachs-Wolf effect. If there is a particularly large and deep void in the path of light in the direction of the cold spot, it could explain at least part of the observed cooling. Therefore, the search for a huge region with a reduced density of galaxies began in the constellation Eridanus. Such an area has indeed been found.
It is called the Supervoid of Eridan. In this direction, the density of galaxies is below average, and the distribution of matter differs from neighboring regions. At first glance, it seemed that the riddle received a simple and convincing explanation. The light passed through the giant void, lost a small amount of energy, and left a cold trail on the map of the CMB. But the calculations showed a serious problem. The discovered void is not large enough and not deep enough to fully explain the temperature of the cold spot. Within the framework of the standard cosmological model, its influence should be noticeably weaker than the observed anomaly. It can only explain part of the effect, but not the whole stain.
In addition, some studies have questioned the very connection between the Eridani supervoid and the cold spot. These two structures can simply be in the same direction in the sky without having a direct physical relationship to each other. The void is much closer, and the relic radiation came from the boundary of the observable universe. Their coincidence on the celestial map does not yet prove that one structure created the other. It turns out to be a strange situation. A possible cause has been found, but its power is not enough. The math doesn't add up completely, and it is in this difference between the expected and the observed that the territory of bolder hypotheses begins.
The most cautious version still does not require any new physics. A cold spot may be a rare combination of several factors: the usual primary fluctuation of the CMB radiation, the influence of a nearby void, and the peculiarities of statistical processing of the map. Each of these effects has not enough on its own, but together they can make one area of the sky noticeably more unusual than the others. This explanation does not look sensational. There is no collision of worlds, unknown matter, or trace beyond the observable cosmos. There is only a complex overlap of processes that took place at different distances and in different eras. That is why it remains the safest from a scientific point of view. But the cold spot continues to attract attention for another reason. It is among several large-scale features of the CMB that also raise questions.
On the largest angular scales, the map of the ancient world does not look as random and symmetrical as expected. Some temperature fluctuations seem to line up along a certain direction. There is a slight statistical asymmetry between the two halves of the sky. There are other deviations that can be accidental, a consequence of residual pollution from the signal of our galaxy or the peculiarities of data processing. Each such anomaly does not separately destroy the standard model of the universe. The problem arises when several oddities appear on the largest scale of the map. This raises the suspicion that our understanding of the early cosmos may be incomplete, or that there is an effect in the data that has not yet been properly accounted for. One of the hypotheses that can explain the cold spot without referring to other universes is topological defects. In the first moments after the Big Bang, the universe expanded and cooled rapidly. Physical fields could move from one state to another. Such transitions are theoretically capable of leaving special configurations of energy in space, a kind of traces of early phase changes. One of these possible traces is called a cosmic texture. It is not a material object in the usual sense. Texture does not have a solid surface, a specific shape, or a fixed position. It is a tense configuration of the physical field that can gradually shrink, become unstable, and collapse. If a similar process occurred in the early universe, the rapidly changing gravitational potential could affect the photons passing through the region. Some of them would lose energy, forming a large cold area on the map of the CMB. The shape of the cold spot in some models does resemble a possible trace of the decay of such a texture. This makes the hypothesis interesting, but not confirmed. To verify it, it would be necessary to detect other similar structures or an independent sign of the existence of topological defects. So far, there is no such convincing evidence. There are also more speculative ideas related to the quantum nature of the early universe.
At the very beginning of cosmic history, all observable space was in an extremely dense and hot state. On such scales, the usual separation between quantum physics and gravity ceases to work. To fully describe those conditions, we need a theory of quantum gravity, which does not yet exist in a complete and experimentally confirmed form. Some models suggest that the earliest quantum states of space may have left large-scale traces in the CMB. If the initial fluctuations were not entirely random or retained unusual correlations, this could create distinct regions that differed from the standard statistical distribution. The cold spot is sometimes seen as a possible example of such an ancient quantum fingerprint. However, this idea does not yet provide a precise and unambiguous prediction that could be verified by observations. It only shows how little is known about the first moments of the cosmos. But the most famous and most controversial hypothesis is associated with a completely different picture of reality.
According to the theory of cosmic inflation, in the first millisecond fractions of a second, space experienced a period of extremely rapid expansion. In an almost unimaginably short time, the microscopic area was magnified many times over. This process could explain why the visible universe is so homogeneous, why its geometry is close to flat, and where the initial density fluctuations came from. Inflation agrees well with many properties of the CMB, but the physical mechanism that caused it has not yet been precisely established. There are many models, and some of them lead to a particularly unusual consequence. Inflation could not end simultaneously in all space. In some areas, rapid expansion stopped, energy passed into ordinary matter and radiation, and the history of a separate hot universe began. In other areas, inflation continued. Then it ended somewhere else, creating a new region with its own Big Bang. This could be the process that is called eternal inflation.
In this picture, our cosmos is not the whole of reality, but one of many expanding regions. Each such region is sometimes described as a separate bubble universe. There is space in between, continuing inflationary expansion, and new bubbles can pop up again and again. This is not a confirmed fact. There is no direct evidence for the existence of other universes. Even eternal inflation itself does not occur in all models and remains the subject of serious debate. However, if such bubble universes do exist, another possibility arises. Early on, the two expanding bubbles could collide. The contact between them should have caused a change in the energy distribution in the collision area. If this happened before the formation of the CMB radiation, the trace could have been preserved on an ancient map of the sky. It could look like a large circular or disc-shaped temperature anomaly. That is why the cold spot is sometimes called a possible trace of the collision of our universe with another one.
This idea sounds impressive, but today it is not a proven explanation. The coincidence of the general shape of the spot with one of the possible models of collision does not prove anything. Similar structures can arise for other reasons, and the parameters of the theoretical model can be changed to obtain different temperature profiles. To make the hypothesis more serious, one cold patch is not enough. Additional features are needed that are difficult to explain by a random fluctuation, supervoid, or topological defect. One of these signs may be a special structure around the spot. Depending on the model, the collision of bubbles can create a certain temperature distribution.
a cooler central region, a transition boundary, or an annular profile. A specific trace in the polarization of the CMB radiation is also possible. Polarization stores information not only about the temperature of ancient light, but also about the direction of its oscillations. It may contain details that cannot be seen on a normal temperature map. If a polarization pattern is ever found in the cold spot region that exactly matches the independent prediction of the collision model, this will be a much stronger argument.
So far, there is no such confirmation. Moreover, the search for similar traces throughout the sky did not give a convincing result. Individual candidates have been discovered, but none of them have achieved the kind of statistical reliability that would allow them to claim contact with another universe. Therefore, an honest scientific position remains cautious. The cold spot exists. It was confirmed by independent observations. It really looks unusual, but its origin is unknown. Perhaps we are just looking at an extreme result of random temperature fluctuations. It is possible that part of the effect is created by the supervoid of Eridan. Perhaps several ordinary processes overlapped and gave rise to an anomaly that seems more mysterious than it really is. It is also possible that the spot is related to the physics of the early universe, which the current model does not yet fully describe. But moving from this possibility to the claim of a collision of universes would be too big a step. And yet, the opportunity remains.
If it is ever confirmed that the cold spot did indeed come into existence as a result of contact with another bubble universe, it will change more than just cosmology. The very meaning of the word universe will change. Today, this word refers to the entire totality of space, time, matter, and energy. Everything that existed after the Big Bang, and everything that can be causally related to us. But in the picture of eternal inflation, our observable cosmos becomes only one area of a much larger reality. Other bubble universes could have arisen with different initial conditions. In some of them, the physical constants could differ. The force of gravity, the properties of elementary particles, and the behavior of fields could have led to a completely different evolution. On some of these worlds, matter may never have gathered into stars. In others, the atoms could be unstable. In some places, the expansion could have been so rapid that galaxies would not have had time to form, and some regions might have had conditions that allowed for complex structures whose nature could not be described by known physics.
But all this remains a theoretical possibility, not an established picture of the world. The main difficulty of the multiverse is its verifiability. If other areas are forever separated from us by expanding space, direct observation may not be possible. Then the theory runs the risk of being too flexible. Almost any result can be explained by the existence of a suitable universe with suitable conditions. That is why the trace of a possible collision is so important. It could be a rare instance where another realm of reality has left an observable imprint within our cosmos. The cold spot doesn't get attention because it already proves the existence of a multiverse. It is important because it is on the border between a measurable fact and several completely different explanations. One small area on the map of the most ancient world links statistics, the large-scale structure of the universe, gravity, quantum physics, and the theory of inflation. Each possible explanation leads to its own idea of the origin of the cosmos. If it's a mere fluctuation, the cold spot shows how easily human perception sees a mystery in a rare combination of random data.
If the cause is a supervoid, then we have one of the largest structures in the nearby universe whose influence on ancient light was stronger or more complex than modern calculations predict. If the spot created a topological defect, it could be the trace of a phase transition that occurred in the first moments of cosmic history. And if it is associated with the collision of bubble universes, ancient light retains the imprint of an event that occurred beyond the usual understanding of space and time. But even if the cold spot once gets a definitive explanation, the story itself won't end there. The CMB also contains other features that do not yet add up to a completely clear picture. Some of them may disappear after more accurate data processing. Others may be traces of processes that took place long before the appearance of the first atoms. Each new map of the ancient world clarifies the known parameters of the universe, but at the same time opens up new questions.
Particularly important is the distinction between a true physical anomaly and a rare statistical coincidence. When one particular spot is examined, its unusualness can seem very high. But if you look at the entire sky using a variety of measurement methods, it's almost inevitable that you'll find at least one area that looks exceptional. The more signs are checked, the higher the probability of detecting a random combination that looks like a trace of an unknown phenomenon. This principle is called the multiple search effect. It doesn't mean that cold spot is necessarily random. It only makes you more cautious about loud conclusions. It is necessary to consider not only the probability of the appearance of such a structure, but also the probability of the appearance of any other structure that could seem equally unusual. This is one of the main difficulties of cosmology. The universe is only available for observation in one instance. It is impossible to repeat its birth, change the initial conditions, and see how often cold spots appear. It is possible to create computer models, generate thousands of artificial maps of the CMB radiation, and compare them with the real sky, but any model is based on certain assumptions. If these assumptions are incomplete, the statistics can also be misleading. The modern cosmological model describes the universe with amazing accuracy. It explains the expansion of space, the distribution of galaxies, the origin of light chemical elements, and the basic properties of the CMB. It is based on ordinary matter, dark energy, and early primordial density fluctuations. But most of the contents of the universe still remain unknown in nature. Dark matter does not emit light and is detected only by gravitational influence. Dark energy is associated with the accelerated expansion of space, but its physical essence has not been established. The mechanism of inflation has not been found either. Even the exact shape of the initial fluctuations is inferred from models that work well, but do not yet provide a definitive description of the first moments of the cosmos. Therefore, any major anomaly becomes a possible indication of the missing part of the picture. The cold spot may not be a mistake of the standard model, but the result of a poorly understood interaction of several known processes. For example, a primary fluctuation, several regions of reduced density at different distances, and weak secondary effects that occurred during the movement of light through a changing cosmic structure can simultaneously contribute to the observed temperature. The light of the CMB radiation has spent almost the entire history of the universe on its way. During this time, it passed through the gravitational fields of galaxy clusters, voids, and huge filaments of dark matter. Its trajectory was slightly curved. The energy could change. The original drawing was gradually distorted, although most of it has survived almost unchanged. It is extremely difficult to separate the primary signal from everything that happened to it later. An additional difficulty is created by the Milky Way. Between the Earth and the distant CMB is our galaxy, filled with interstellar dust, gas, electrons, and magnetic fields. All these components radiate in the microwave range and are able to hide a weak cosmological background. Observations at different frequencies are used to clear the map. Dust radiation, synchrotron radiation of charged particles, and other sources have different spectral properties. They can be separated from the CMB signal, although this procedure is not absolutely accurate. Even a small residual error can have a particularly strong impact on the largest areas of the map. That's the scale of the cold spot and other known anomalies. However, the coincidence of the WEMAP and Planck results shows that the spot cannot be easily explained by a single instrument error. The two devices use different technologies, frequency bands, and processing methods. Both found the anomaly in approximately the same place and with similar characteristics. This strengthened the confidence that the cold spot was indeed present in the data, but confirming the existence of an anomaly is not the same as understanding its origin. Future research should focus not only on temperature, but also on other properties of ancient light. Polarization is especially important. It occurs when photons are scattered in a medium with a certain directional distribution of radiation. As a result, light receives a weak orientation of oscillations, which carries additional information about the early universe.
A temperature map can show the same spot for several different physical reasons. Polarization can vary. Statistical fluctuations, topological defects, and bubble collisions do not have to leave the same pattern of directions. This is why more sensitive polarization measurements can greatly narrow down the explanations. If no special polarizing structure is found in the cold spot region, some exotic patterns will become less likely. If a pre-predicted profile appears, which is difficult to obtain randomly, interest in new physics will increase dramatically. But even such a result will require independent verification. The history of cosmology knows many cases when an unusual signal first seemed revolutionary and then disappeared after improving instruments or detecting an unaccounted source of interference. At the largest scales, it is particularly difficult to rule out systematic errors because there are a limited number of independent regions of the sky available.
For small structures, thousands and millions of examples can be observed. For spots a few degrees in size, the entire sky contains significantly fewer independent areas. Statistical conclusions become less reliable, and each individual anomaly acquires too much weight. Therefore, the cold spot may remain a mystery for a long time. It is impossible to see it closer, like a galaxy or nebula. The device cannot be sent to it. It does not have a clear distance until its physical cause is known. This is not an object located at a certain point in space, but a feature of the distribution of temperature on the surface of the last scattering, superimposed on all the matter located between this ancient surface and the Earth. The spot can simultaneously be a trace of a very distant process and the result of a relatively close structure. These options look the same on a two-dimensional map of the sky, but mean completely different stories. If it originated on the surface of the last scattering, its cause dates back to an era when the universe was about 380,000 years old, or even to an earlier period of inflation. For small structures, thousands and millions of examples can be observed. For spots a few degrees in size, the entire sky contains significantly fewer independent areas. Statistical conclusions become less reliable, and each individual anomaly acquires too much weight. Therefore, the cold spot may remain a mystery for a long time. It is impossible to see it closer, like a galaxy or nebula. The device cannot be sent to it. It does not have a clear distance until its physical cause is known. This is not an object located at a certain point in space, but a feature of the distribution of temperature on the surface of the last scattering, superimposed on all the matter located between this ancient surface and the Earth. The spot can simultaneously be a trace of a very distant process and the result of a relatively close structure. These options look the same on a two-dimensional map of the sky, but mean completely different stories. If it originated on the surface of the last scattering, its cause dates back to an era when the universe was about 380,000 years old, or even to an earlier period of inflation. However, even such clarifications do not yet guarantee a complete explanation. The standard model predicts a certain strength of the integrated Sachs-Wolf effect. Some observations of the large-scale structure sometimes showed a stronger signal than expected, but the statistical reliability of these results remains a matter of debate. If the actual effect is indeed stronger than the calculated one, it could indicate unusual properties of DARP energy or a deviation from general relativity at gigantic distances. So, the cold spot again leads to fundamental questions. Perhaps the problem lies not in the void itself, but in how gravity acts on cosmological scales. General relativity has undergone many tests and describes gravitational phenomena extremely accurately. But most rigorous tests apply to the solar system, binary stars, black holes, and relatively local regions. On scales of hundreds of millions and billions of light years, gravity is studied through indirect observations. If its behavior is even slightly different from the standard equations, light passing through huge voids can change energy differently than models predict. This does not mean that the cold spot already indicates altered gravity. Such a version requires much more evidence, but it shows how far an attempt to explain one cold area on a map can go. Each path faces its own problem. The statistical fluctuation does not disturb anything, but it leaves a feeling of an extremely rare coincidence. The supervoid exists, but its expected impact is too small. Topological defects can create a similar structure, but no such defect has yet been confirmed. The collision of bubble universes is allowed by some theories, but there is no direct evidence for the existence of bubbles themselves. The altered gravity could amplify the effect of the void, but the anomaly alone is not enough for such a conclusion. Not a single explanation has yet become final. Perhaps this is why the cold spot retains such power. It is not the brightest, most massive, or destructive structure in the cosmos. It is a slight difference in temperature, almost disappearing against the background of ancient radiation. But behind this subtle deviation are questions about the boundaries of observable reality. The most surprising thing is that the information about a possible event in the early universe could have remained almost unchanged for more than 13 billion years. Stars were born and died. Galaxies collided, absorbed each other, and changed shape. Black holes accumulated mass. Space expanded, and dark energy gradually began to determine its further evolution. Against the backdrop of all these processes, ancient photons continued to move through space, preserving the faint pattern of an era when no stars yet existed. This figure is now available for measurement. Every small deviation in temperature becomes a message from the past. Most of these messages have already been decrypted. They talked about the age of the universe, its composition, geometry, and expansion rate. But some parts of the map seem to contain symbols, the meaning of which is still unknown. A cold spot is one of these symbols. Perhaps it does not hide anything unusual. Sometimes a rare accident remains just a rare accident. The universe does not have to create only typical structures. Among the huge number of fluctuations, one should be the deepest, largest, and most noticeable. But if there is a separate physical process behind the spot, its value may be much greater than its weak temperature signal. It is able to show that the initial conditions of the universe were more complex than expected, may reveal an unknown property of dark energy. It can become the first indirect sign of an ancient topological defect, or lead to an even more radical conclusion. Our cosmos was not completely isolated at the time of its birth.
And yet, regardless of what the final answer turns out to be, the cold spot has already changed the way the universe should be studied. It reminds us that even the most successful scientific theory is not the last page of a book. Each generation of telescopes makes the cosmos clearer, but at the same time opens up new mysteries that no one has noticed before. Perhaps in a few decades, more advanced space observatories will make such an accurate map of the CMB radiation that the origin of the cold spot will become obvious. Perhaps new surveys of billions of galaxies will make it possible to restore the full three-dimensional structure of the cold spot. So far, none of these options have become a reality. Today, only one thing can be said with certainty. The cold spot really exists,
It has been confirmed by independent observations and remains one of the most unusual features of the CMB radiation, but its true nature is still unknown. This means that we are not facing a solved mystery, but an open scientific question.
Sometimes these are the most important questions, not because they immediately change textbooks, but because they force you to look for new ways to test old ideas. The history of science has repeatedly shown that the greatest discoveries began with a small discrepancy between observations and expectations. A slight deviation in the motion of the planets led to the discovery of new laws of gravity. Unusual lines in the spectra revealed the structure of atoms. Barely noticeable fluctuations in the CMB radiation made it possible to understand how galaxies were born. Perhaps the cold spot will one day join this list. Or perhaps it will remain a rare statistical feature of the vast universe, a reminder that randomness sometimes looks incredibly convincing. This is the real value of science. Its task is not to choose the most effective explanation, but to gradually discard all options that do not stand the test of observation. Even the most beautiful hypothesis is worth nothing without proof. Conversely, the most unexpected conclusion may be true if it is supported by the facts.
Today, there is no evidence for the existence of other universes. There is no evidence that the cold spot is a trace of a cosmic bubble collision. There is no confirmation that it was completely created by a giant supervoid, and there is no reason to completely reject any of these possibilities. Therefore, this story remains unfinished. Somewhere on the oldest map of light, there is a region whose temperature is only a few tenths of millionths of a degree lower than the surrounding background. It is impossible to feel or see such an insignificant difference with your own eyes, but it has given rise to one of the most far-reaching debates in modern cosmology about the origin of the universe, about the nature of space, and about whether there could be much more beyond the observable cosmos. Sometimes the deepest questions are not born from grandiose explosions or giant galaxies. Sometimes one tiny cold spot in the ancient world, which has been traveling through the universe for almost 13.8 billion years, is enough. And perhaps it is in this barely noticeable imprint of the past that the answer to the question of how big the reality really is.